Hi everyone, welcome back. Today I'm going to be sharing lesson 8.2. Let's see if it works here. 8.2, yay. What is solubility? Go. You can do it, PowerPoint. Yes, okay, great. All right, so today's aim is 8.2. What is solubility? And I'll talk you through the demo. We'll do the question of the day. I'll go over the homework from the night before, homework 10, and then the lesson, and then I'll kind of show you what the activity would have been like if we were in class, and then the homework is homework 11. So the question of the day is, which of the above are true liquid solutions? Explain. So yesterday we learned 3 criteria for a true liquid solution. The first is it has to be see-through. You have to be able to see light pass through it. The next is that you can't have anything that settles out when you let it sit. And then the third was that it can't be filtered. So if it doesn't meet those criteria, then maybe it was more of a heterogeneous mixture. Or maybe it was even a pure substance, not a mixture at all. So definitely not a solution. So let's look at these 3. So A, milk. Light can't pass through it, so that means it's not a true solution. Maybe it is still a mixture, though. It's definitely still a mixture, so it must be more heterogeneous. B, light can pass through it. I don't see anything that's settled out. If we imagine this has sat here for a while, and it looks like it could probably all pass through a filter, like nothing would get stuck on top of the filter. So that means B is probably a solution, a liquid solution. C, light definitely can't get through it. So this is, again, not a solution. So the only one that would pass the test would be potentially B. All right, let's take a look at last night's homework, homework 10. So I'll just go over some of the answers, but if you have questions about any part of it, you can always email me. All right, the box below shows that what occurs on an atomic level when a mixture of aqueous sodium chloride is made by dissolving 3 grams of NaCl, sodium chloride, in 30 milliliters of water. So here we've got the sodium chloride. Little orange thing is the Na, sodium, and the big blue one is the chlorine. We can see that when they break apart in water, the water does this sort of surrounding it thing and keeps it apart from the other ion, chlorine ion, sodium ion. So these 2 ions are completely broken apart from each other. So that shows me that this is a true solution. It's dissolved down to the ionic level. So A, do you think this mixture would pass through a filter? Yes, because it's a solution. B, is this a solution? Yes. Why? It's dissolved down to the ionic level. C, if it is a solution, what is the solute? Well, that would be the things that is being dissolved. So that in this case is sodium chloride, NaCl. And then which is the solvent? That would be the water. Number 4, when a teaspoon of sugar is added to water and stirred, the sugar dissolves. Number 6, which sample of matter is a mixture? Well, this is H2O, solid, not a mixture. That's just a pure substance, just pure H2O, one compound. Same with this one, except it's liquid, but it's still just one substance, water. And it is made of 2 elements, but they're in a fixed ratio, chemically bonded together. So that's a compound, a pure substance again. Same with this, another pure substance, liquid sodium chloride, that's melted salt. It has to be really hot, but it is a thing. But this one, you'll notice it says AQ. Remember, that stands for aqueous. So that means the salt is dissolved in the water. So 2 different things. This one is a solution. It is a mixture. All right, so if you have other homework questions, please email me. And maybe we can set up a Zoom meeting soon for your questions too. So our lesson today is 8.2. What is solubility? And remember, you can pause at any time to look back at something or write down notes or whatever you like. All right, so I was going to do this demo for you guys. What does styrofoam do in water and in acetone? You can probably picture what it does in water, right? You drop a piece of styrofoam in the water and it floats. In acetone, it dissolves. It looks like it kind of disappears. So what we're talking about today is why. Why would it react a certain way in one substance and differently in another? Or in other words, why is it more soluble in some things than others? Solubility is what we're talking about today. Solubility is how well something dissolves in something else. So what do you think determines that? Why would something be really soluble in acetone but not soluble in water? Well, to get into that, we want to do a quick review of some terms. So let's remember what these three things mean: nonpolar molecule, polar molecule, and ionic compound. So these are going to have to do with bonds and with shape. So first, let's look at molecule versus ionic compound. Molecule, remember what kind of bonds that is? Yes, covalent. That's where you have two nonmetals or more than one nonmetal sharing electrons. You make a molecule. And nonpolar means it's totally symmetrical. So there's no one end of this molecule that's going to be pulling on the electrons more than the other. Totally nonpolar, like this example, carbon dioxide. Covalent bonds, they're sharing the molecules, and the molecule is symmetrical, so there's no negative or positive end of this molecule. All right, polar molecule also has covalent bonds, also made all of nonmetals, but it's asymmetrical, and its shape gives it polarity. So this element has really high electronegativity, so it pulls on the electrons more, making this end of the molecule more negative and this end more positive. So nonmetals but symmetrical, nonmetals but not symmetrical. And then of course ionic means what kind of bonds? Right, ionic. So we've got a metal and a nonmetal, and that'll make a crystal like sodium chloride. Okay, so the concept here, why do some things dissolve well and others, has to do with this idea of like dissolves like. So what do we mean by like dissolves like? Well, you might think we mean things with similar bonds dissolve each other well, but it's actually not true. Things with similar attractions dissolve each other well. Here's what I mean. Nonpolar solutes dissolve really, really well in nonpolar solvents. For instance, have you ever gotten grease on your hands and you try to rinse it off in the water? What happens? Right, the water just slides right off of it. If you've ever worked on a car and gotten oil or grease on your hands, or you tried to do dishes, and there's oil in the pan or butter on your hands, it doesn't just rinse off very well, right? You need to use soap. And that's because soap is also nonpolar, like the grease. So you use a nonpolar solvent and it dissolves that nonpolar solute really well, and then you can rinse it off with the water. Like dissolves like also means that ionic solutes dissolve really well in polar solvents. So ionic and polar, they have totally different bonds. Ionic solutes have ionic bonds. Polar solvents have covalent bonds, but because they both have charge, they're good at dissolving each other. So ionic solutes turn into ions that are positive and negative, and polar molecules have an end that's kind of negative and an end that's kind of positive. So you can see again, this is like the picture from your homework. The polar solvent surrounds the ion and keeps it from reconnecting, rebonding back to the other ion. It keeps them separate. It keeps them dissolved. So this example is salt and water, sodium chloride and H2O, and I have a bigger picture on the next slide. Yeah, so here we have the negative end of the water molecule, which is the oxygen end, right? H2O. The negative end surrounds the positive ion. And then here the positive ends surround the negative ion and keeps those ions apart and keeps them dissolved in water. Like dissolves like also means that nonpolar solutes do not dissolve well in polar or ionic solvents, and vice versa. So nonpolar goes really well with nonpolar. Ionic and polar go really well together, but they don't mix. Anyone have a guess what this picture is of here on the slide? This is fat in water. So kind of like the example I was telling you about, if you try to do dishes, and there's like grease or fat on the pan and then you rinse it, it's like the fat all clumps up. It doesn't just dissolve into the water. That's because fat is nonpolar and water is polar. So they don't dissolve each other. They kind of almost repel each other. And this actually comes in really handy in the human body. Question, do you have any nice organs? Yeah, imagine how awful it would be if your organs just dissolved, right? That would be no good. Luckily, they don't. How come? That's right, each organ is covered in a layer, phospholipid bilayer, you might remember from biology, that's nonpolar. And that nonpolar layer protects your organs and keeps them from dissolving in your blood, which is polar. That's just one great example, but these are all over. And hopefully this is reminding you guys of when we studied bonding, right? Mystic sand just like repelled the water. Great. Okay, so now we're going to get into the why a little bit more. Why does like dissolve like? So let's see if you remember these 3 types of intermolecular forces. We studied this back in the fall. We studied bonding. There's 3 types. There's dipole-dipole force. That's between 2 polar molecules. There's the hydrogen bond. That's between 2 superpolar molecules that have a Fon element, F, O, or N. And then there's weak intermolecular forces, which are between 2 nonpolar molecules. So we've got an example of one of each on the screen. You can guess what they are. So here we've got 2 polar molecules, so that's dipole-dipole. Here we have 2 superpolar molecules. They have a Fon element. Nitrogen is one of the most electronegative elements, F, O, or N. So that makes this superpolar. So they would be attracted to each other with a hydrogen bond between the N in one molecule and an H in another molecule. And then these guys are both nonpolar, so their only option is the weak intermolecular force, which is like when they get a momentary dipole, all the electrons kind of shift to one side for a moment, and it becomes a little bit polar for a moment, enough to stick together. All right, so we're going to review those 3 here, and we're going to add just a little bit extra for solutions chemistry. So the first one is the same as before. The weak intermolecular force, that's the one that you get when you have 2 nonpolar molecules. Number 2, the dipole force. This is the one between 2 polar molecules. We're going to add to that and make 2 categories. One would be dipole-dipole, when 2 polar molecules attract. Excuse me. And then ion dipole is when a polar molecule and an ion attract. So this first one could be like HCl and HCl, 2 polar molecules. And then this could be like water and salt, a polar molecule and an ion. And then the last one is going to be the same as before. A hydrogen bond is still a dipole force, but super strong because it's between a hydrogen in one polar molecule and a fluorine, oxygen, or nitrogen in another polar molecule. All right, so for a solution to happen, you need to have one of these intermolecular forces between the solute and the solvent. Otherwise, it won't really make a solution. So in this activity we were going to do in class, we were going to play Will You Be Soluble? So you'll be given a substance identity. You figure out whether you're nonpolar, polar, or ionic, and then you try to make as many solutions as possible. And for each one, find out which type of attraction is it that makes you able to dissolve each other. So I just want to walk you through the first example and let you figure out the second one on your own. So example number 1, we've got 2 people. The first person is magnesium bromide. That's what they look like. Person number 2 is chlorine gas. This greenish gas here. So we're going to figure out, will those make a good solution? So to figure that out, we need to figure out if they are going to like dissolves like. So are they similar or not? So are they nonpolar, polar, or ionic? Person number 1 is magnesium bromide. So what do you think? Nonpolar molecule, polar molecule, or ionic compound? That's right, ionic. We've got magnesium's a metal and bromine is a nonmetal, so that's ionic. How about person number 2, the chlorine gas? Nonpolar, polar, or ionic? That's right, nonpolar molecule because chlorine is a nonmetal. So if person 1 is ionic and person 2 is nonpolar, are they going to attract each other? No, ionic and nonpolar do not go together. They are unalike. So the type of attraction is no attraction. They would not make a solution. All right, let's have you try example 2. So person 1 is water. Person 2 is lithium fluoride. What do you think? Will they make a solution? So person 1, water, that's polar. Person 2, lithium fluoride, metal and nonmetal, that's ionic. Polar and ionic do go together, and their type of attraction will be ion dipole. Ion dipole. So that would make a great solution. Awesome. Thank you guys so much for being here again today. And homework for this lesson is homework number 11. And let me know if you have any questions. Have a wonderful rest of your day.